This is now a contradiction because W1 is shorter than W. But we define W to be the shortest possible walk of odd length. And so there cannot be a shorter one. And so since there can't be a shorter one, there can't be any of this figure eight action. And therefore, it is a cycle. Woo! Good. Flip the camera, because what this means is that all I have to do to establish that there's an odd cycle is to produce a closed walk of odd length. And so now we say, by the lemma, there is an odd cycle. Or G has an odd cycle. G has an odd cycle. Because there's this odd walk, or there's a closed walk of odd length. By this lemma, G has an odd cycle. But that's a contradiction with G having no odd cycle. Cool. Woo! Take a second to digest. Which is supposed to be cool. Next, I make a new picture for the other case. Why can there not be an edge B1, B2? Well, it's kind of similar, right? Now if there's an edge between B1 and B2, this is, again, A, and this is B. What is wrong now? The graph is connected, so there's a walk between every 2 points. So in particular, there's some kind of walk between B1 and V, right? But how did B1 end up in big B in the first place? B1 ended up in big B because the shortest path from B1 to V was even. Therefore, the shortest path must be of even length from B1 to V. But now, what about B2? How did B2 end up in big B? Again, it ended up in B2 by, I'll just draw them solid line. B2 ended up in there because the shortest path from V to B2 was of even length. And so now, I can claim that V B1 B2 V is a closed walk of odd length. Agree? Okay. And now, by once again invoking the lemma, oh man, this is taking us forever. What do we know? G has an odd cycle. Contradiction. So, we have shown that this really is a bipartition. Yo.
That's only for the case where B is not B1 or B2, but you could also, right? Yeah. But if B is B1, then you just have a contradiction with your earlier classification. Because the shortest path is that.
Oh, he says that somehow I used the fact that B1 and V were different from each other. Did I even really? I'm not sure if I even did. Because it's still going to be, if B1 is V, then I just have V to B1.
You don't have any close walks.
Oh, I have a separate contradiction because then if they're both in B, then their shortest path between them is 1, is what you're saying. And that can't be true because dude, that's worth mentioning. Yeah, I did sort of assume that B was different from B1 and B2. Okay, good. Whoa, that was on one of my list. That was the number 2 of my list of things to do. Interestingly, we are still on, however, number 1 of my list of things to do, which is going over the homework.
It's fine.
So that's pretty cool. Someone take a beautiful picture of that board, well, or not, and then wait 2 minutes and someone erase it. What's left? Do I need to do the rest of these problems? 19A and 19B?
Wait, we didn't do 19, 18.
Oh, we did do 19.
I didn't assign 19?
I think you.
No, I didn't write it down.
I thought I did, right? Yeah. Good. What does 19?
Oh, here, you get it.
What is 19 say? 19 says, yo, let G be a simple graph with n vertices, and that G contains an independent set of size k. An independent set is a whole bunch of people that are not friends with each other. Agreed? Yeah, good. Simple graph with G contains an independent set of size k. What is an upper bound on the number of edges in G? Oh, so if these, so they're n vertices total, right? Is that what it says? Yeah. And there's a k-sized independent set. Well, then what that means is that there are these k vertices which are not all friends with each other. So I guess the biggest the number of edges could be is if the other n minus k vertices are all connected to all of these guys and also all to each other. That's it, right?
Yeah, it's n choose 2 minus k choose 2.
Yeah. So here there are k vertices, and here there are n minus k vertices. And so the largest possible number of edges that this graph can have, if there are k people who are not friends with each other, is if every other possible friendship obtains. And how can that be? Well, there's n minus k choose 2 ways for all of the other people to be friends with each other. And also, each of them is friends with all of the people who are not friends with each other. I think I've done that correctly, right? So k times n minus k. Is that what you guys did? Or you did something else? Or you just subtracted? A better solution would be to simply take n choose 2 and to subtract out k choose 2. But you guys were mumbling when I wasn't listening. I bet these two are like the same though, are they? I bet it's true, because right, isn't this just like k, n minus k, but then this is like plus n, this is like not obvious at all. N minus k minus 1 over 2. But if I like stick a 2 over here, then what the hell happens now? Someone like algebra that out. Or you can just trust my combinatorial reasoning.
That's a good combinatorial proofs problem, right?
It is a good combinatorial proofs problem. Thank you for that. I was being really dumb on purpose. Good. Can I stop now? Good. All right. Woo. Good. We go straight to part 3 of the homework. Part 3 of the homework, part 3 of the lesson, which is to go over part 2 of the homework. So, part 2 of... just laugh at me what I say. It's kind of like weird. Alright, good. Someone erase that board. Here's what happened last class. As we mentioned at the beginning, not a lot because I just drew a bunch of crap on the board, but what you were supposed to learn is the difference between all of these little words, man. Walk is just the general term for like a sequence of edges through a graph. A trail, ET for VP, means that you don't repeat edges. Path, ET for VP, means you don't repeat vertices. A walk is closed, okay, we're good with that. A circuit is a closed trail, and a cycle is one in which the endpoints are the only repeated vertices. So what's the difference between a circuit and a cycle? Is like the 8 thing, right? I feel like that's the only difference. But this would be, wait, let me make sure I'm not doing it wrong. This would be, if this is like V1, V3, V4, then a this is not a then V1, V3, V4, V1, V2, V1 is not a cycle. Agreed? But it is a circuit. I hope I did that right. A circuit is a closed trail. So, V1, V2, V1, V3, V4, V1, or just the same one. It is a circuit. To me, that's like the big difference between them, right? A circuit doesn't repeat edges. A cycle doesn't repeat edges either. They're both closed, but in a circuit you can repeat vertices, though you cannot repeat edges.
You can't get to this, you can't repeat an edge without repeating a vertex, right? So one of these is like a subset or something.
Yes, every cycle is a circuit,
Yes.
but not every circuit is a cycle. I find this hard, which is why I assign so many little problems that we're just like, do this again. Okay. The other thing that happened in this section was the introduction of all these concepts, which I think are like chill though, like connectedness. What does it mean to be connected? There's a walk between every two vertices we've been talking about. So that's like a very nice, elegant definition. We can also ask questions like, how connected is a graph? Or like, how tight-knit is your friendship group? Suppose you're planning like a prom week, and you're like, oh damn, am I inviting 5 people? We're all gonna hang out together, but is there like one person who's only friends with like one other person? And then when their one friend goes to the bathroom, it's like awkward because they have no one to talk to, right? That graph is connected, but it's not like that connected, follow?
Honestly.
Okay, so we can measure the degree of connectedness. It's not just a binary thing, connected or not. And there's this concept of a cut vertex and a cut edge. A cut vertex is or a cut edge rather, is what it would take to make your graph unconnected. This is a strange shape I've just drawn here. So, like, in other words, if this friendship were to suddenly disappear, the graph would not be connected. Cool? Say cool. So we say this graph has edge connectivity 2. A more connected graph would be one with edge connectivity, sorry, what did I say? Edge connectivity 1, I meant to say, yeah. I was thinking ahead. This has edge connectivity 1 because by deleting one edge, we can make it disconnected. Dustin?
There's only 5 minutes left.
Of class? On the camera, on the battery?
Yeah.
Okay, that's bad.
And like,
There's
not
only
like we have
10 minutes left.
Only
class.
7 more minutes than that.
So should we just do it? We're only be taking just like 3 people anyway, like screw them, good. Wait, actually, if we're doing this properly, we should. Who knows, we might do something really important at the very end. Can you use this key to open that thing and get out the extension cord and then plug it in using the battery that's behind my rolly chair? Just put all that sentence together and you'll figure out what to do. Good. So wait, as I was kind of trying to say, but I was like not doing a good job, this graph is like more connected, right? Because now there is no one person who you have to worry about, being all alone when one person leaves. This graph has edge connectivity 2 because it would take 2 destroyed friendships to make this graph disconnected. Follow? Yo.
It's like equivalent to the minimum degree in the graph.
I don't think it's the minimum degree because, for example, you could have 2 independent sets that weren't even connected at all, but they had high degree or something. Oh, maybe it is the minimum
No,
degree.
it's not.
It's not quite the minimum. Wait, hold on. Let me think. Let me think for a second. Because here's a counterexample.
I like the
to that.
Romeo and Juliet graph.
Yeah. That's it.
What's the Romeo and Juliet graph?
Yeah, Romeo and Juliet are friends, and nobody else between the 2 families is.
Yeah.
Oh.
Wait, what are you guys talking about?
It's Romeo and Juliet.
Oh, yes, that's,
Is that what this is?
Yeah, because those 2 are friends and nobody else. Yeah.
Who are, Romeo and
Those 2
Juliet,
are
you're
Romeo
saying
and
are friends.
Juliet, yeah.
Ah, I see. So this is like Romeo, this is Juliet, this is Juliet,
Yeah.
and like Capulets and Montague.
Yeah.
Oh yeah. Do you know that all the English teachers refer to Romeo and Juliet as R and J. It's really hilarious. We were at a staff meeting a couple of years ago, and we were talking about like suicide prevention, and suddenly like there was a moment in which that meeting could have just ended, and then it just would have been over. But instead, some pesky people started asking like weird questions, and then we just opened a whole other can of worms. It was like, what about like all the books we read in which like suicide comes up like often in like the standard high school canon, and then some English teachers like, yeah, like in R and J, for example, and I was like, oh my god, I can't believe you just did that. All right. So anyway, good. It goes in like here. Earning that health credit. Okay, good. So wait, is this a good counterexample?
Yeah.
Because here, all of the vertices have degree 3 or up, but it still has edge connectivity 1. Cool? Okay, what you are talking about, however, is a different measure of connectivity, which is not edge connectivity, but vertex connectivity, which Gossip just calls connectivity. But I think we should probably all call it vertex connectivity for sort of clarity. But vertex connectivity says how many people would have to leave before your graph were disconnected. So now, like for example, if like Romeo dies, then this is like disconnected, right? And so,
Spoiler.
yeah, or, sorry, yeah, good. Okay, so wait, do I need to go into more examples, or can I just leave it at that? Right? It's the number of vertices that would have to be removed for your graph to be disconnected. Okay, and you can come up with all kinds of little examples of graphs with certain vertex connectivity and certain edge connectivity. I think it's also not true, let me just be careful before I say this. Something like what you said is sort of true, which is that the minimum, the edge connectivity is like at most the minimum degree. In other words,
Oh, yeah. That makes sense.
You'll never have to
remove more than that.
you'll never have to remove more edges than the minimum degree vertex. Okay, these concepts are not really like deep, so I don't think we need to like go into them all. Zum, boom, and that was it. No, that wasn't it. There's a whole nother part of this like lesson called adjacency matrices. Did I assign any problems on this to you? Good, perfect. What did I assign, however? Like a bunch of little problems on various other things? Is that true? It was mostly like a lot of little problems and then like one hard problem, right? Which was number 1? Or 2. Yeah, number 2 is just, I think was just hard. Although certain people, I found it hard, but then other people found it easy, I don't know. Let's go. Number 2 says, is the camera over here? If G is a graph, then either G or G complement is connected. Okay, so theorem. If G is a graph, then either G or G complement is connected. Okay, this feels very true, I guess. Everyone is sort of friends or enemies, and you make a graph of all the friendships. Then G complement is the graph of all the enemyships. And now, for any 2 people, okay, let's just begin. I've written this out over there, but I don't know if I need my paper or not. Maybe I can just okay, here's what we can do. First note, the complement of G complement is back to being G again. Okay, So to show that either G or G complement is connected, without loss of generality, let G be disconnected. And what I'm now going to show is that G complement is connected. I claim this suffices because, well, if G is disconnected, then G complement is connected. Thus, well, there are three cases, right? They're both connected, in which case we're great. G is disconnected, then if I can show that G complement is connected, then I've shown that one of them is connected, right? And if it's the other way around, that that G complement is disconnected, well, the exact same logic shows that G is connected. So this covers it all. Okay. Did you guys follow that? That was like not perfectly explained. Okay. Woo! All right. So what's up? Well, if G is disconnected, then G has at least two components. This was kind of the hint, right? So since G is disconnected, G has at least two components. Call them C1 and C2. Okay. Well, there are two cases, and there may be more components. Okay, so there are two cases to consider. There is the case where V and W are in the same component. Okay, so okay, sorry. Let G be disconnected. I'm going to prove that G complement is connected. How do I prove that G complement is connected? Well, I invoke the definition of connected, which is that there is a path between any two vertices. Cool. So take arbitrary vertices V and W in G complement and show there's a walk. Why must there be a walk? Well, there are two cases. There's the case where there are these components, and V and W are in the same component. And then there's the other case in which there are these components, C1 and C2, and V and W are in opposite components. This was Gossett's case. Okay. Well, let's notice that these components refer to G. So I'm showing G edges, not G complement edges, I guess is the way to put it. Okay, well now we know that there are at least two complements, like non-empty complements or something, right? So there has to be at least something in this complement. And the thing is that because, components. There's at least something in this component. Well, as these vertices are in separate components, then there just isn't an edge between V and X, right? Because they're in separate components. In fact, there's no walk whatsoever between V and X. So there certainly isn't an edge directly connecting them. Similarly, there's no edge between W and X, because there isn't even a walk between W and X. Okay? So if there's no edge between V and X, and no edge between W and X in G, well then there just is an edge in G complement from W to X, and from X to V. So there's your walk connecting W and V. Follow? And finally, if they are in separate components, then again, there's no walk between them. So in particular, there's no edge between them. So if there's no edge between them in G, then there is an edge between them in G complement. So in both cases, I've showed that there's a walk from W to V in G complement. How are we doing? Good. We succeeded in going over all the homework and learning one new thing, and that was it. Basically a total failure. But we did learn a lot. I think we learned a lot. Is that too much detail or just enough? Just a lot of stuff. Just a lot of stuff this unit. Alright. Good. Goodbye.
So fucked up.
Yeah.